Okay, now I want, before reading sequentially through the chapter, I want somehow to summarize sort of what I take out of this chapter, and maybe have a more higher level discussion about what's going on over here. And once maybe we do step by step, then we can also read more through the sequential output of the chapter. Now, one thing which I like about this chapter, this is about engineering. Sort of in the previous chapters, we basically discussed in depth one building block. So we had, say, the transformer structures. We said, how does in the box, how does the transformer work? And how do we use this transformer structure to do some entity recognition? Okay, now we have a bigger system which has many parts which work together and which need to be put together and which also have to deal with each other's mistakes. So that if one part is built on machine learning and makes a mistake, how does it affect the following on parts of the system? Does the next part of the system correct for the error, or do they amplify the error? And this is interesting, so that you have some engineering going on over here. And I want to show something over here. Give me just 1 second. So the interesting part over here is the engineering aspect. Let me show something. I put this into Google, and so the standard application of the chapter is we ask a question to Google, and we get the answer right over here. Now, this answer is correct. However, that's not the only place where Google uses this question answering algorithm, because you see in all the snippets which we see down over here, they highlight the answer to our question. So they use the question extraction, where you have a question and you have answers, and you find within the answer where do we have the correct in the document, where do we find the correct answers. They show us for each snippet that try to do that. Now we see always the same answer. However, sometimes there will be mistakes. So for instance, over here, this is a different number. And this is actually a question of a different answer. The question over here is, when will Python 3.10.1 will be available? And over here also the first answer is also not the right answer. It answers a different question. And if we look at the document, we see over here that the statement over here answers the wrong question, and the correct answer actually appears over here, but the algorithm did not find it. So the reading comprehension was not good enough to, if you look at this text, you see that the correct answer is down here, and around over here that's a false positive. Okay, now, but if you look at the results, Google put it into a system where, even though we get the wrong answer over here, it does not crush our user experience. We see, okay, I find the answer here and I see the context, understand it answers a different question. Maybe it's actually interesting for me. So Google built a system which is sort of, even though at some point we get the wrong answer along the line, but the system is stable enough to provide a usable user experience nevertheless. Now, there is also another point over here, that if you say that it's a powerful idea that you can use artificial intelligence, neural networks, to answer a question. You ask a question, you get an answer. And you have many ways to do that. So if you have extractive answering, which we see over here, where we just don't try to give the answer, but we try to find the answer and to just highlight it. But there is also, say, a generative question answering, which is more complicated and today less powerful. So you can say, well, one idea is more impressive, and the other idea is more stable. So if you do the engineering, you can balance so that you the different things you can say, well, we want to have a good user experience, let's try first to work with something which works and which provides a good result. But maybe we introduce the idea of generative question answering in some points where we see that we can provide value, but not in all questions. Sort of, so, and that's something which I find very interesting. Sort of, how do you build useful systems with these components, and how to understand how things fail, and how do you create value with end-to-end value with that. So this chapter is somewhat more complicated than the previous chapters, and there are some high-level things which I think are very interesting to discuss. Now, I must admit that one aspect of the chapter I didn't understand well, and I glossed over. And if nobody else knows it better than me, then I just skip that part and I tell you what it is. If anybody has understood that part of the chapter, I will happily hand over the microphone. And that part is the statistical evaluation of how good our predictions are. Sort of a score to say the recall is so many percent, the precision is so many percent. And I tried to understand it. I didn't spend a lot of time over there. And I felt that the things didn't really, I didn't understand. Maybe I've some claims that maybe the explanation was it is strange over there. So I skipped that. If somebody understood that part of the statistical evaluation, how well the system works, okay, we can go into that. Now that's for the big picture. Now let's go one step down. So if you have, let's go back to this. We see that the question answering system over here in Google, the chapter discusses a system which is similar to what we see over here. Okay, there are different variations of the idea of question answering, which are different, but that's what we built in the system. So we see that there are different stages. The first stage is we get an user input. We have a query. The second stage is that we get many different documents which are relevant to the answer. So we have 1, 2, 3, 4, 5. It's a standard search engine which produces these answers. It's one stage. And so we hope that all or most of these documents contain the answer which you're looking for. The next stage is that the system extracts from each of the article the correct answer, and it is then highlighted. Now there's another step which is not discussed in our chapter, but which Google obviously does. So once we have all the answers from the documents, we have Monday over here, we have October 4th, then they come up with a decision of which answer should be the one answer to show. And they're showed over here at the top. That's one other step. So we have input the query. First step is retriever. Take many documents and retrieve all the relevant documents. Then you take from each document a reader, which reads the document and tries to find the span that answers the question. And then we have post-processing, which says, well, given all these answers, let's show the one which is correct. And this, our chapter did not go into that part, but it's part of a decision-making system. No. Now, at this stage, I want to discuss some technical details. For instance, one point, okay, two things. First thing is the retriever which finds these documents. We have different approaches which we can use. One approach is a classical approach to check for keywords. We can say Python 3.10 and released, and we can find documents which have these words in them, and we can hope that these documents show also the answer to our question. And this is a classical search engine. Alternatively, we can use deep learning a vector representation of documents or of paragraphs within the document and see what of these vector representations are close to the query presentation. And maybe we can combine these two approaches. Maybe. No, the chapter doesn't do this. I'm not sure whether Google does this, but we at least two different approaches how we can extract the build the reader. Now, our chapter says we can try both directions, and they both work. So there is one place where we can use transformers to use the sentence embedding and use them in the query extraction framework. The next stage is always using transformers, where we say, let's try to find the answer span. And over here, I want to say that our model has a certain size limitation. So how do we deal with the fact that a document can be much longer than our model can process? Now, we will go into the details more in a moment, but one thing we can say is because we're only looking for short answers pieces, the problem doesn't get we can chunk up each document into paragraphs or into overlapping pieces and look at each overlapping piece independently. So the point which I see is engineering wise that because we are looking for short answer, chunking up a long document into many small pieces and work on each small piece independently does give us a good result. So we can say that in this particular question, if you want to have extractive query answering with short answers, that the fact that the documents can be long is not a problem because we can break up any long document into many small fragments and run the model on each small fragment independently, which is not the case, but which we discussed last week for text summarization. You can't make a summary just by looking at one small fragment. You need at least to have a sizable site to summarize something. Okay, so what I'm saying is over here, I'm still talking about engineering, so that it's interesting to evaluate how different limitations or different errors affect each different stage. How many options do you have? You can use a more traditional algorithm, you can use a more new algorithm, and maybe you can make an intelligent choice which one is the best in each situation. And obviously this is a lot of work. So now I want to make something more about the engineering over here. And there are many points where you can make a mistake. And what's exciting about this chapter over here as well, that there is this haystack library, and which shows that the Hugging Face ecosystem is not just Hugging Face having one side where you say we have data, we have models, and we have discussions, but you have also other players in the whole world which expand the Hugging Face in ecosystem from the outside. So you have the haystack company, the library. The company's, I forgot the name of the company, but maybe I recall in a moment. And they said we take Elasticsearch, which is a community by itself. We take some other engineering players, and we take Hugging Face, and we create one bundle from this, which makes it easy to use, so that you can, with in a few minutes, build a prototype, a baseline, just by putting this, taking the standard default configuration and run it as we did in chapter over here. And because they chose to connect with the standard API from Hugging Face, that you can use any of their models. So you can, just with a few lines of code, pull together a working implementation of a full question answering pipeline with all the pieces together. And this is really exciting. Obviously, when you want to do this for real, you still have a lot of places where this can go wrong, and you need some tuning and some fine tuning and some adjustments to your specific problem. So it's not easy. And this applies both to the data science world of fine-tuning the model using the right configurations, and also to the DevOps to run them to run these models in production. And I saw that this is both sides are not trivial. So they offer a service, a managed platform where you can run maybe 3 models, and this costs 6 figures of just maintaining the DevOps sites. So we see that sort of the value in in managing such a system, it's not easy. It's not sort of there are customers who pay a lot of money to get this all working and maintained well. But still, we can sort of for demo and also for production, we can get something working just from in a few minutes. Basically, I over here pointed out things which I find exciting about the engineering aspect of the whole thing, and I want now to go more deep into more details. That was putting at a background. So if there are any questions to what the high level things which I discussed right now, I'm happy to take them. But if no, we can go more step by step into the thread of the chapter. So are there any questions so far, or shall I just go more deep into details?
Yeah, happy to go. Yeah, I'm okay for me.
Okay. So, like any good project in data science, this chapter starts with a data set where we say that we choose a project on a data set. And the discussion whether a decision whether we take a closed domain QA system or an open domain system. Closed domain system means that the questions are more similar to each other, and it's more easy to work this way. Open domains is when we have take many domains together and try to put one model which answers all of them together. Now, as you look at so obviously taking one subset like electronics out of the system is easier to succeed. Well, this is what they do in the chapter. So they load the data set, and something which is not discussed in this notebook, but in the chapter, is that you have different data sets. So the sub-QA data set is quite small. So we have over here about 1,300 queries, which is not a lot. And in the academics, you have the Stanford question answering data set, which is much bigger and was used as a baseline for much of the research. And also, we have the version 2 of that and additional data sets. And maybe we spend a few seconds about understanding how these relate to each other and what does it mean for us in the data science. So first of all, our data set is very small, and that's a problem. You can't really train a neural network on 1,300 data points alone. That's not feasible, but we will do something interesting in a moment. B, the Stanford question answer data set was built where we take short documents and ask the crowd to ask questions about this text and to highlight the question answer. And this had a point that every question had an answer. And when we train a model on that, the model can say what is the most likely thing which is related to the question, even if it's a false positive. So that even if you say, for instance, when we have over here, look at the example, we say that this looks like a good answer. It's related. Obviously, this is related to the question which you asked. But when you do that, you create a model, you train a model to even produce false positives because they never saw a question which doesn't have an answer. And this is bad for the end-to-end product, because if you would now the second version of the model, they said also ask questions which have no answer and get the model to recognize we don't have an answer and say I don't have an answer. Now, if you integrate such a model which says I recognize there's no answer in this text, then this model could say we don't use this one document over here. We use only those documents which have the right answer, which improves our end-to-end results. So one point is Stanford question answering data sets is much bigger, and it has a version which trains the model to recognize something is not related. Don't give wrong answers. Okay, so and Google went on to build more data sets for more realistic data question sets where the challenge is more difficult. For our application over here, how does it relate to us? We take a pre-trained model which was trained on the big Stanford question answering data set, and we do not replace the head by a new head. We just use the same head as it is. We just retrain it, fine-tune it on our small data set. And this is an approach which works. Why does it work? We have exactly the same structure. So in our previous examples, where we did replace the small head, it is because we wanted to use one model for a different but related task. Over here, it's the same task, so we don't need to throw away what we learned so far at all. We just to fine tune it as it is. And in this setting, taking a huge data set, pre-trained on a model, and then fine tune on a small data set is something which works. Okay. Now there's also a question: which kind of questions to be asked? Over here, our questions are more, how you say, subjective. That they depend on the opinion, and this has some impact on the quality. How much can you generalize or not? Okay, so the chapter says we download our data set, we look at it, so we see what columns are available, we select those which we want, we look at some examples, and it makes all sense. As a data scientist, you want to understand your data sets well, so you see how many questions are different types, but obviously this doesn't affect the end result. It just affects that we have a better understanding what we're doing. But this is just investigation. Okay. Now, as we see, our notebook so far skips about the retrieval step. So it doesn't go deeply into the retrieval step. It focuses on understanding how does the question answering works. So we can say the presentation of here is that you say we have this whole engineering which I spent a lot of time talking about, and we will talk about in the next step. But for the transformer, the one point where we look how transformer do it is the one piece which is the reader. How do we find that one snippet which gives the correct answer? So how does it work? We basically train the model as a span recognition model. So it's using the same structure with what we already okay. We use the when we had the entity recognition. There in the entity recognition, the task was to find tokens which fall into certain categories, maybe even tokens which can or spans which entities which span few tokens together, and to label each of these tokens to be a location or to be an institution or something like this. And we use the same idea to say what are the starting tokens from an answer. So we want to find the model to label this token is the starting point of the answer. And also, in addition, to say label which tokens are the end tokens of the answer. So we get over here the graphs that we say that if this is the context, and we go back and explain a bit more of the context, but that's the document which we look at. We have a question over here. The question is how much, the question is over here. How much music can this hold? The answer, correct answer over here is 600 hours. So we see we want the model to detect where does it start, 6,000, and where does it end, hours. And we say the correct answer is from here over here. Now the model also says that the one is a very likely start of an answer, and minute is also very likely end of the answer, but not as much as this answer. So that if that answer wouldn't exist over here, the model would give us the answer 1 megabyte per minute, which is actually a wrong answer. And I just tried this before, whether it works. So we see over here, this is what the book computes, and it gives 6,000 hours. If we just remove the 6,000 hours from the context, for instance, over here, that is over there. If we just change the text and we just remove that piece, over here, let's say the context. So the answer depends on the context and doesn't, we remove the number and we compute that text over here. So we see that it actually produces the answer one, so that answer 1 megabyte per minute, and also it gives the wrong answer. Okay. So basically the network structure for this is exactly how we have the network structure for entity recognition, except that we have two separate answers, one for the start and for the end tokens. And also we give an additional answer because in the entity recognition, we have only one text, where we have two texts. We have the question and the context. So we provide another token type IDs mask, which is like an attention mask, which separates what is a question, what is the answer. And this is additional input which that the model can use in order to train the right thing, so that it can say, I can use some of my reading comprehension, some of the decoding of the input to understand the question and to understand the context, the document, and then to find the overlap and point out which tokens are starting and end tokens. Are there any questions about that structure? So I was going to summarize. We have we want to extract a sequence, a span from the beginning to the end. The model structure is exactly like the entity recognition, which tries to predict likelihoods for a token to be in a certain class. And we have over here two different predictions. One is for the starting token and one for the start and for the end. And that's a model of the structure of the model. And in addition, we provide another mask as input, which can be used to tell the model where is the question, where is the answer. Any questions on that? Or shall we go on? I take that silence for no questions and to go on.
I'd say I just have a comment.
Sure.
Which is but you know, the softmax probabilities of the end start and end tag, and how you can, if you don't have the right text, get the wrong answer, just really highlights that. I'm assuming that you better make sure that of two things when you set up a system like this. One, that your corpus of passages or documents are very likely to have an answer in it somewhere. And number two, that your retriever is finding it. Because if those two aren't true, you're going to get a wrong answer, just like you showed right there. Because your retriever, it's not like a retriever has a threshold under which the probabilities are low enough that you know it's wrong, right? You know what I mean?
Now, I want to take it. Okay, the point is, what you said is 100% correct for models which have been trained on the first version of the SQuAD, a Stanford question answering system. This was exactly the system what you said. Now in version 2, they said we want to train the model that if the answer is incorrect, that it says his answer is incorrect.
So no, I was thinking about that, but that's very interesting. So the question is, when you're looking at this image here of this classification of start and end token, how does that translate to this? Does it just have 0 softmax for everything? I mean, how do you know that you've gotten a non-answer when you're
Okay.
Okay,
answer the question. So now first of all, there are two parts of it. One part is I tell you what is the ideal solution, what we want to do, but still it doesn't take away the problem. Sort of, it's the problem is still there. Okay, so but it just makes it better, sort of approach the solution. So when you say in this version 2 of the SQuAD data set, we had many documents. People ask real questions which have answers and labeled the answers in order to train this model with the start token and the end token. And then they also added a lot of data where you had the same kind or the same documents, and the people ask questions which are related to that but do not have an answer. Like for instance over here, when we say when was Python released, so we could ask question 1, was Python 3 abandoned or something like this, or and they said that these questions should get no answer, and the model should then give the start and the end token to the CLS token. So that you should, in a case where there's no relationship, the model should give to the CLS token a very high likelihood for both of these points. So basically,
that's interesting. Why is that?
Now, basically, this means that you train 3 separate models. One model is say, where does the question, where does the answer start? Where does the answer stop? And you have a separate question, separate task to answer: is this related? And if the model sees, I think this answer should be from here over here, but I see it's not related, then it should decrease all the likelihoods over here and push up the CLS token to say, well, it's very likely that the CLS token is the start and the answer. So that this requires the model to develop another step over here, another step of to see whether if there's a mismatch between these 2 points, to say, stop, I don't want to give an answer. And this somewhat works. And if you look at this graph over here, I'm not sure where it appears before, afterwards, that they got better. Yes, so up here. This graph is on the 0.2 version. Sort of the when they started, the version 1 was already at 90%, and now they said, well, let's train models, and they see they got over a couple of years, they got even on this more complicated task to some good scores.
Yep.
Now, I want to use this opportunity to say something. We saw that we had one model with one research approach where they said we have a question answer task is a SQuAD version 1.0, and the first versions had a very low score. So the first models which are built, they sometimes got the right answer, but often not. So then people are working and they got to 90%. They got, wow, we are better than humans. We have superhuman performance, and people can write this to the newspapers and see, well, we have built a neural network which is better than a human in answering questions. Now, this is, we need to understand, this is not the what we saw over here. We saw that you have one data set, and on this one data set, on one specific test, a certain model had a better answer than certain people doing that. But it doesn't mean that the model is better in answering questions. It's just working better on this data set. So then we say, well, actually the model is cheating. It's not understanding the question. It's just trying to find the most relevant span, which is good, but it's not what the human is doing. It's lacking a part of understanding whether it's good or not. So we created another data set and we saw, wow, the performance drops down to 70%. Okay, they're not better than humans. Then you work on this and we say, well, now on this data set, we get again superhuman performance. Does it mean that we now are better than humans? And I'm claiming no, because one thing which humans are today much better than neural networks. We make mistakes, but we know how to live and how to handle the mistakes which we make. So the thing is that when a neural network makes a mistake, it just makes a mistake, and that's a mistake. But when a human makes a mistake, he has so many controls, so many experience, what to do not to fail, even though I make mistakes. And that's something sort of in every sort of any statistics like this completely does not look at the capability of the system, how to handle things which are not modeled by this data set, not so it's getting superhuman performance on such a statistical set does not mean that we are better than humans. It just means that on a specific narrow challenge, we are sort of overfitting, or we're understanding that challenge better than a human. I can recall that when I was very good in mathematics when I was in university, even now as a child, I liked mathematics, and I learned that if I make a computation longer than one page of paper, for sure I make a mistake. I make mistakes, I know that. I can't stop myself making mistakes. Now, in the end, I wrote a PhD thesis of like a few hundred pages, and they were good. So what did I do? So I learned early on how do I compensate for my errors. Sort of that and I automatically, so when I make a computation, if it's longer than a page, I double check. And if the double check works, I continue. If the double check doesn't work, I go back and I fix it. So when I was a child, I was excited about mathematics and I did what the model does. I succeeded. When I saw, well, when I get longer than a page from the computation, it doesn't work. So I developed a new capability of correcting my own, correcting my own mistakes. And I did this a few times, and now I can write PhD thesis of a few hundred pages, and everything, and the end result is correct. So I make some mistakes in the middle, but nevertheless, the end result I can take responsibility over here. And we see over here the same process happening slowly and slowly. And to get to superhuman performance in one step doesn't mean that AI is surpassing humans. It's making one step similar to what you do when you're a child. So when you got up and you got to walk and run, you make one step over here and learning something to get to human performance. And then when you fall down and when you do something else, you start to dance, you do this again, you start and to get to human performance again. And so when AI wants to really say replace humans, they don't have only to succeed in one of these challenges, they also have to make the sequence of getting more and more levels of self-control. Okay? This was a very long answer to your question. Shall we continue? I take this for yes. Okay, now in the book, 1 second. Let's see where we are. We have over here the point of dealing with long passages. So we see how long are the passages. We see that some of them are very long, but most of them are short. And we decide that over here, this is not a problem because we can chunk up the text and have overlapping images, overlapping frames. Now, why is it good over here? Because we are looking anyhow for short answer, which you normally can recognize from the context. So for instance, over here, if you look at this results, we see that say that's the input which you given to the model. And you can see that answer over here, you can recognize from the context whether it's right or wrong. Now, and we see actually at this example, really things broke down because the right answer would be you have to look at this beginning and then at the end, and to see that really this together, this beginning and the end, you get the round. And so it could be that the model didn't make the whole competition, but it could also be that you have one span which goes from here to here. The next span goes from here to here, and the model never saw the necessary pieces, and so to get the whole answer. But for most of our over here, for most of our use cases, chunking things up is good enough. So because that's what we what we need over here. So how do we chunk up? So we have a separate. We basically have a sliding window which slides by a stride, step by step. Now, I want. Do we want to go into the details how exactly the parameters have to be put, or can we just take this as a discussion over here that we say we take the text, we have overlapping windows, and we run the model on each of them, and then we select the best answers. Now over here, actually coming back to our discussion, we will have windows which do not have a good answer, but we still can compare them all together, and we can take the one window which has the most confident answer. So over here, if a window produces a low confidence false positive, that window doesn't know whether that's good or not. But if in the same text you have a much better answer, you know to use the better answer, not the worst answer. So shall we, any questions about that, or shall we go on? So let's go on. So over here we see the question. Okay, I go on. If you have a question on what we discussed so far, please just interrupt me. And
yeah, my question is just a simple question. Does anybody knows like how to create this question and answering data set, like to train a machine, to train a model, how this kind of data set is created?
This has been discussed in the paper, in
Okay.
the chapter. So I tell you the answer. If you look at page 171, you see the Stanford question answering data set. And you have the footnote 5 at the bottom of the page, which is the article which explains that. And on the next page, 172, we have two more footnotes about two more data sets, which are version number 2 and the natural questions. So let me tell you what they did. They took Wikipedia articles and cutting the articles into small pieces, which is exactly what we do over here, which makes sense for this point. So you take a long Wikipedia article, you take a paragraph, and you have as many paragraphs as you want. Okay. Now you send these paragraphs to the Amazon Turk or any other crowd of people who can help you, and you say, for instance, this is, let's take this as an example of an article. So you ask them, ask a question about this paragraph which can be answered. So, for instance, I could ask over here this rolled up. My Android phone and can be rolled up. What is? They work great with. They can be rolled up, or they work great with my Android phone. Okay, so you can say they work great with my Android. Okay. This is an answer. And what's the question? Does this, what is it? Is it the headphones? Do the headphones work with Android? So you say, bring up a given the, or how's the bass? You can answer, that's the question with over here. It has great bass response. So you say, ask a question, highlights the answer, and do this, create this data set. This was version number 1. In version number 2, they said do the same thing, but also ask questions which have no answers. And about the Google data set, they didn't, the chapter over here, the book does not go into details how they created this, but we have the article on the bottom. Did I address your question? You are muted, so
Thank you. Thank you.
I think you can also, this is a little out there, but you can also use a, you can use a T5 model or a doc to question model. And you could generate questions from your content. And I mean, maybe that's a way you then people have reviewed, because then you sort of have an already created data set that needs to be refined. Or you can use, the expert guys have this, a method, I forget what, MMR or something, whatever. It's a method for doing, for training without having a training set. And you could probably use that set of model generated questions to train. They use kind of like contrast of learning, sort of. It's a little complicated, but so you might be able to do this without actually having to pay people to do to create a set like that. Anyway.
I want to analyze it. I want to. This is a very interesting discussion here. So let's spend 2 minutes to discuss. First of all, you're saying that you can use a model like T5 to create a data set over here. Okay, now this is important because you have any shortcut, any way to make your work more efficient with data, it saves a lot of money. Sort of today, data sets can be worth a few $1 million. Like, say, for instance, they created the data set for legal documents, and this cost $2 million. All the training models today can be very expensive. So any improvement which you can make in the process can easily sort of, if you can reduce the expense by a few $100,000, you can justify an engineer's work for a year to do that. So over here, you said you can create at least part of the process by now model which exists. And definitely this is an idea which needs to be taken into account, and this can save a few $100,000 definitely and put into place. Now, but I want to say, how was this model created? How did T5 learn to create questions from the data? And it's quite feasible to say that they were actually fed with this kind of data set. We say this is the answer, this is the context, these are the questions which we found. And now instead of training him to say, find the answer, you can say, take the same data set, find the question. And what you can see over here, you could say, maybe you can start with one data set, like for instance, the squad data set, to train a model to create questions, and then use the same model which you trained now on a different corpus, like on a whole of the Wikipedia. And instead of having a few 100,000 rows, you can now create millions of rows of many questions. But maybe now you need some review to see which questions are right, which questions are wrong. And so maybe you can use this as a way to create the data at much more scale faster. Now, one other thing is you said create questions, but does it also create the answers as a T5 model, or does it just ask the questions? And if you would just have the questions, then you would still need some tagger to create the answer.
Yeah, I don't know. I'm just putting things together in my head. I mean, if you could generate the questions for the document, then you could probably get the spans out of them.
But I'm thinking, even if you only get the questions, you could still save maybe 10% of the expenses of this project, and you could still,
yeah, of course, semi-automatic, automating it. And also, what I was trying to connect the dots to with expert folks is actually, I just posted it, GPL. So and it's a way of using. I don't know. I can't explain it all, but you get results back. It's a way of doing this without of fine tuning your model, your similarity model. But I don't know. I'm just throwing ideas together. I think that's the way things are going now. It may take a while to get there, but.
Great.
What-
Can you please post this link in Slack in addition to the chat?
Done, dude. I beat you to it. I knew you were going to say that.
Thank you very much. Okay. Shall we go on or any more questions?
We can go on.
Okay, thank you very much. Now, this here, we now only worked on the reader, that part, and now we take the bigger picture, and I spent a lot of time at the beginning of the call talking about essentially this picture, where you say you have many documents, which could be many web pages, or it could be many paragraphs of one document, which are many windows, and you take all of them and you make a retriever to select those which may be relevant. And as Darren pointed out, if you make a bad job over here, then the reader has a lot of rubbish to guess, and you get bad answers. But if you make a reasonably good job over here, then maybe the reader can still give a lower score to those documents which are not really relevant, and you get in the end still a good answer over here. So the answer post-processing is not so much discussed in our chapter, but that's what we do. And Haystack gives basically for the whole pipeline a solution, which you just need to configure. You just have to put together. And for the retriever, you have two options. One option is a classical option to use a standard search engine with Elasticsearch. And you can also alternatively use a dense paragraph representation, which is basically creating a embedding for each paragraph and compares them to the question. And it's all made for you. You can install it. Now, when you run this notebook on Colab, you take out this page, because we have two different ways to start Elasticsearch, and this one works and this one doesn't work. So I have commented it out. And besides, Elasticsearch works, and you basically take all the documents and just put them into the search engine. And you can search, for instance, here you can have a query. Is it good for reading? You have a condition that you only want to find answers which have the item ID over here. And you use a retriever where you say the query is over here. You take the top 3 answers, and any document which does not have a structured item ID which you're given will be rejected and will not be used. And this is standard search engine technology, and it works. Are there, and depends sort of, you have two options over here, what underlying engine you use. How much do people want to understand more about how this elastic step of the retriever works? Or shall we just take it as that's a black box building piece which we just use in the model? I take the silence as going on. If you have questions, please interrupt me, and when I continue, sort of, I'm happy to take any comments or questions. Also, for the reader, we have different options, which basically are different open source libraries. One is the farm reader, which I believe is created by this DeepSet. The company is called DeepSet. I didn't tell it before. The company is called DeepSet. DeepSet is a company which creates the farm reader and the Haystack model. And so the farm reader is their implementation of combining these models from Hugging Face together with this technology. But there is also Transformers readers, which I believe is created by somebody else. And they say, well, this is our solution. It's better. It's better integrated, and it works better with what we need. But you can also use the transformer readers. It's an option for you. And the book chooses rightly that the that library because it's better integrated. How is it better integrated? So one key point is that the transformers reader normalizes the results for each chunk, which means that you cannot compare multiple chunks or multiple documents against each other. So you could have a lower confidence for some documents, but it will normalize that difference away. Whereas the farm reader says, well, we don't want this, so we don't do that. In our context, we want to get real confidence which the model tells us, and we want to take the one answer which has the highest confidence. So because this is what we need in our integration, so the farm reader does it out of the box. Whereas if you take the transformers readers, it has been designed initially for some other use case, and they do some step which over here is not the right thing to do, and as a result, it's better to use the farm reader, unless you really need the transformers reader for some other benefit which they have, which I'm not aware of. And this is engineering, sort of your you can make a baseline by just taking the default values and get something up and running in a minute or in an hour. But if you build the business on top of this, you will have to dive into all the small details, and you may find out that you may want to write a new open source library to support your use case, what you actually need. Okay. So over here, we just plug it in and we get the answer. And now we put them together as the pipeline, which takes the reader, which is the search engine. The retriever is the model over here. We just plug them into one QI pipeline, which says take both steps together. And so we can run a query on this, and you get the answer. Is it good for reading? We get the answers and so on. So far, that's how to build the system. The next step is we see that these answers are not very good. Why are they not very good? Because the model has been trained on the Stanford question answer dataset, and we are asking on a different dataset, which is another point where we see that if they would be really as good as humans, they should be able also to answer different kinds of questions with a similar approach, but they're not. So they're sort of overfitting on what they trained on. So for improving the QA pipeline, we want to understand how good are we, and that's a step which I skipped. So basically, what I can say, we have a pipeline sort of hacking. DeepSet provides standard building blocks to do that evaluation, and just plug them together in the same way as you plug the research engine together with the transformer model. You just can plug together the pipelines to get the evaluation. And but nevertheless, I didn't understand it. Okay, I didn't understand what happens below the surface, and also actually it in some points it crashes in the GPU. But the next, so that's, I'm big on this. So don't, if you ask questions, you can discuss it. But if you want answers, you need somebody else to provide some insight how this all works. But what is really important over here is that I'm saying, when I run this document, a side note, GPU was crashing a few times. Predictably, when I wanted to build the model, I used to say the to load the data in the model, but when I run it again, it worked. This was a error which went away, but over here, that error, which we see over here, which is in the evaluation, it always breaks for some reason, that cell. And so I didn't run this. Okay, but the thing which you want to do is to fine tune. So when you fine tune over here, you basically have to create data in a format which is you have two approaches. The approach which is paragraphed, which our book does, is we have a fine-tuning function built already in the haystack library. So create the data exactly in the format which they need and run the function. Now, you could do something else. You could take the data format as you have, and you could train it yourself. You can build that functionality yourself step by step, and try not to make any mistakes, and debug it. And you could retrain the model by yourself. So, beauty of the approach of Hugging Face and of of Haystack is that they did the work for you. You get at least the baseline by just plugging the pieces together, and the APIs are quite usable, quite nice. But in this case, it requires us to understand what is the data, how does the training data look like, what's the structure which they want, and how to put it into the right pieces. So the data structure looks quite complicated. Why? Because it's an industry standard. So that's what academia uses for at least some of their work, and because of that, that's what's supported in the engine. I did not go into all the details. I just believe that if I plug everything together as in the code, I will get a fine-tunable model, which is essentially built on ideas which we had already seen in previous chapters. So I am superficial over here. So any comments, even questions, are highly appreciated.
So I just want to check with other people because it's already an hour. So if we are fine to continue, or we can, for me, I'm okay, but what do you think, if we can continue next week or we can continue now? So
we can also wrap up I don't have a lot more to tell. So the question is whether we want to take maybe 5 or 10 more minutes, or whether we want to stop now and spill over to the next week.
Yes, exactly. But if people are fine, we can continue. Just want to check because so that maybe people will not leave. Yeah, okay, we are fine, I think, everyone. So we can continue.
Okay, so basically I'm finished with my presentation over here, except for the generative QA, which I don't really have, can summarize what's said over here. So let me quickly summarize what we have seen so far, and then go on. So the summary of the whole chapter. I would say the chapter discusses in some way, the chapter focuses on one application. And the application is supposed to be shown over here. How do you create this kind of an output in the example of the examples which we have over here, which means you have a question, you have a set of documents, and you chunk them up, and you want to find the answers which represent this. And that a host of challenges. One challenge is how to extract the question from a text. This is transformers. And so we discussed how to create a data set for training the transformers. What challenges do we have? What do we do with false positives and so on? And this is one part of the pipeline. Then you have another part of the pipeline, which is the retriever, which takes from all the documents which you have the most relevant ones. And we discussed that it's important to do job over here. And then we saw that you have a library which puts this nicely together, which is Haystack, where if you do a default or a standard approach with a few lines of code, it's really it's less than 20 lines of code, you can get all of this running with standard parameters. We saw that if you take a model which has been trained on one data set and you use it for different tasks, the performance goes down. And you have an API, API to fine tune it. And this is how I do all the details over here. And the beauty is over here, like fine tuning, that if you have a model trained on a huge data set, you can transfer it to a new data set, even with fine-tuning on a small data set, because you don't throw away anything. So that we don't throw even the head, we don't throw away. Okay, now that's one story of the book. Now the other point is that at many points the book says there are more interesting things which are in the around this topic. For instance, there are many references to how the data sets were created, about the technology where can dig deeper. And at the end of the chapter, it says, well, the question answering has also the generative approach. What is generative approach? Where you say, we don't want just to find a short snippet out of the code which gives the answer. We want a full answer. We want the model to create an answer. So what we do is, instead of the reader to have a model which predicts the end, and start and the end, we put a generator. We take a transformer which creates a text. Now for that, we need the training data set which actually has well-formed answers. So that's more complicated to create the training set. It's more complicated, more difficult to train as well. And also you have, so it's more, this is more difficult to get right. And if the questions which you have really need just an answer which is a snippet which is in the text, it's an overkill. But if you need results which are more intelligent than just pulling out chunks of the text, then that's the right way to go. And we see over here that there are different ways to do this. The simple approach is to do exactly what we did so far. We take all the documents, we select the ones which are relevant, and each independently you try to create an answer. You take it takes this as context, and you train the model to extract from the query the answer to say something something right. A more powerful approach, but also more difficult to get right, is if you say maybe that we have a couple of documents, and one document contains one part of the answer, and another document contains another part of the answer, and we want to combine these pieces to one story. This is a more difficult problem, but it can be solved. So you take all the documents which you have, provide them as an input to the generator, and produce an answer together from them. And this links back together how the transformer architecture works with attention. We can actually say we have many documents, many representations, and we can pay attention to the relevant information even if they come from different parts of the document. So this sort of fits together. Now, my impression from this is that this is much more difficult to get right than the simple approach of getting a span, predicting the beginning and the end of the token of the answer. And as we see, the results over here are not very nice. Sort of if you ask our question, the answers are not better than extracting something from the text. We can also see that the model wasn't really trained on the kind of questions. If you ask a question which is easier, which more similar to what the model was trained on, we actually get somehow reasonable answers. So this is like an outlook of how the world, how the domain can progress. And in the books they say, well, maybe by the time we discuss this in our book reading session, the real world looks different. Maybe it's already taking over the world by storm. I haven't checked. So if anybody knows what's the state of the art in this field, share some insight.
Not in training a sequence to sequence full transformer, but you can actually skip everything, all of this, and use GPT-3 to do question answer, literally. I don't know what circumstances it's better at than others. You can fine tune the GPT-3 model on OpenAI's playground quite easily, with just a couple hundred documents. So in a lot of circumstances, I don't know what a lot means, but a reasonable number of circumstances, you might be able to solve your question answer systems without having to do hardly anything. And that I would recommend being familiar with how you do question answer in GPT-3, particularly the instruct model on OpenAI, to see that, because that's the best one there is out there. And if it can work there, you may want to, not go through a lot of other all of this stuff we just looked at. I don't know what percentage of time that'll be, but And there are applications now, there's money going into this, a lot of venture capital, and there are people building businesses around chatbots that just simply use the, I guess it's the, I don't know, we call it the decoder or the generator side of the transformers and just using GPT-3 that way. It's crazy.
I have three points to respond to what you say. First of all, I feel we should at some point put into that one session, which you should take, and you should tell us how all of these things which the book discuss can be done with GPT-3. I would sort of challenge you. Could you, I get the story, but you say, well, you just ask the right prompt and you get the right answer from GPT-3. And I would be excited if you could take one session, 1 hour, and just say, well, we have over here so many chapters. One chapter is this, token extractions. The other chapter is translation. Other chapter is query answers. And if you just could maybe put together some examples, you say, well, this is a query which you ask, this is the answer which you get, see how good it is. I would be excited to see that, and I think it's very relevant. That's first point. The second point is that I read an article by I believe, maybe by somebody, I'm not sure whether it was from DeepSet or from another company, but he said he took a OpenAI model sort of in the alpha or beta testing phase when they could run it for free, and he runs some serious data on that, and he evaluated the performance, and he saw that it was performing not according to the state of the art of other models which are available. Sort of it was on, in some cases these big models are much more expensive but worse than the real state of the art which you have. So
I think what that came out of was not the prompt stuff, that was using the embeddings. You know, they're like a 1200
yes, you're right,
embedding.
Yeah,
right. Yeah. And
no,
some people do claim that those work like better for clustering and stuff. I haven't used their stuff for embeddings yet. I usually use Expert or something like that.
No, I didn't intend to shoot down GPT-3 by saying that there are people who claim it's not good. What I'm saying is that if you want to use that in your business, you have sort of, in the same way I said over here, you can in 20 lines build a full search engine by just taking a haystack pre-configured. And you say you can take GPT-3 and you just have one API call and you get the answer. And the thing is that if you use this for a presentation, that's all you need to do. But if you want to use it for business, you have to dig in, how does the system work and how does it fail? You have to check where does it produce good answers, where not, and you have to come up with a plan how your business works in the case when the model gives the wrong answer. And
absolutely, that becomes even more critical. All of that stuff you were talking about earlier becomes even more critical with these generative models.
That's engineering.
Yeah.
And the point is that I would be excited if you could make a presentation with two parts. One part is to make basically takes a book, each chapter, takes 3 prompts from where you say, I answer the question with GPT-3, the question which is asked in the chapter, I bring up an example and see how it works. And the second point is to see how can things fail, sort of show some examples where it didn't work. Now, the other point about GPT-3 is, it's expensive. Sort of, in many cases, you have models which are maybe not as good or require you more engineering to get right, but they are orders of magnitude cheaper to run, or maybe you can even put them on the smartphone of your customers instead of running them on your servers. And this cost difference can break a company.
Oh yeah, of course. It has its place, yes. And getting a better feel for that's important if you're an NLP practitioner, because if there is a place for it, it simplifies things. So yeah, I'll do something. I mean, I don't know if it'll be a full session worth, but I can do some simple things, you know, and I can also talk about a project I'm doing at work where I'm using GPT-3 to auto-generate marketing sales emails. So, you know, it's more realistic situation. But yeah, I'd be glad to do that. So, Yeah, you guys just let me know when you want to schedule that in. And maybe it could be combined with, maybe somebody else has something on QA, whatever it is, or on anything in any of the chapters that they have experience with, or that they went down some rabbit hole and researched. If anyone else has a little, we'll call these lightning, maybe they're not super lightning, but we could turn it into a little bit of a share lightning session where we each do, you know, a 10, 20-minute share, not each, but if there is someone else who's interested in sharing something specific related to what we're doing, they could do that along with me, you know, and if there's 4 of us, we could do it as sort of a lightning session. So I don't know. Either way, I'll do it. But if anyone else wants to join in and do something that's just of particular interest to them for some reason, that's fine with me too.
My impression from your comments is that you have much more than 1 hour to present, but it's your guess. How do we decide when to do that? Shall we take this offline to Slack, or shall we decide right now? I would be excited if you do this next week, or if you need more time the week after, or whenever.
How many chapters do we have left?
We have about 5 chapters.
And when are the guys, the authors? I have no questions for them now, but when are they showing up? When is that?
How many weeks do we have before the questions? Did we already invite them, or is it still flexible?
Now we have 4 chapters left, and I think it's a good time maybe to invite them. Maybe we can invite them maybe next week if you are all good. Because that's
yeah. I mean, I don't know. What do we have to ask them at this point? I mean, why are your notebooks fucked up sometimes? We definitely have that question.
Yeah, that's the plan, that we can after chapter 7. And today we discussed chapter 7. So we have 4 more chapters to cover, and we can invite them, or maybe after that, if you have something that as just you discuss maybe next week, then we can invite them week after, or the other way around. What do you think?
I mean, I think that we have 4 chapters. We shouldn't take a sideways step at this point with my stuff. I mean, I think we should at least do another chapter or 2 and then schedule me in. In terms of having the authors come, I think that's for the group to think about, because we just need to make sure we feel like we have enough to discuss with them. My feeling is we don't right now, but that may not be anybody else's feeling at all. So what do you guys think? A couple more chapters before we get the authors scheduled in, or what? We need a poll is what we need, I think.
Now, okay. I agree. I feel not ready, and actually I'm not sure. So I would like to have some more time to think up good questions, and I didn't do the homework for that. Okay. So I would be, just for having good questions, I would prefer to postpone the QA session with them, and that's because I didn't do my homework. So I think if I would have read better and I would have written down questions, there are questions, but I didn't do the work.
Okay. Darin, when are you free to take us through what you've just discussed? Next week?
You know, I could do it any week. I just don't want to. I mean, we still have 4 chapters left. I mean, I don't want to. Maybe there's a short chapter in here where, let's assign next week's, and then maybe it ends up being I can be ready when there's a short. Is there a short one in here maybe where I could then fill in the rest? Or you can schedule me anytime you want. I just think we have momentum, and we need to get through these chapters.
Right. Anyway, we can follow up via Slack. Yeah, I think.
Yeah, schedule. Just tell me when you want to schedule me in, and I'll say yes or no. Okay. That's fine.
Yeah. All right. Okay.
Okay.
Thank you very much.
Who schedules that? Who makes this question? Or so I want to know who takes responsibility for inviting Darin for the call.
Inviting for the authors.
Darin. So there are 2 questions. So what I would like to have is that, say, if you decide when to invite Darin, then that's okay with me or somebody else. And B, I would be happy to postpone the questions, the Q&A session with these authors a bit, to give us a chance to generate good questions.
Yes. So the first one, inviting the authors, we can postpone it anytime. Even we can say end of the book, so that we have gone also the chapters. That's fine. maybe we can give that in next week, this same time, to just discuss about the GPT stuff he is just talking about. So Darren, I think if you're fine next week, we are going to listen to your presentation about the stuff.
Okay.
Yeah.
Next
Jacob,
week is Darren. Great.
okay. Okay. Thank you for volunteering, and I hope it will be.
So next week I'm not doing the chapter next week.
Yes, exactly. Yes, not chapter.
Oh,
Just
okay.
wander around and see. Yeah.
That's great.
We can
Do you want to try to assign that chapter now too, though? Just so we have the next. Does anyone want to take that chapter now?
Yeah. So the next chapter is David. I already messaged David because last time, I think 2 weeks, he was here, and I chatted him. You say, yeah, he will do the chapter. So right now I sent him a message via Slack that, hey, the next week is your chapter 7, but he hasn't responded because I just sent him. But I will follow up to say that it is week after next, because Darren, you will present the next week, so he will have more time also to prepare. Great.
You got it all in check. Awesome, dude. Thank you. That sounds good.
All right. Thank you very much. Yeah. So if anyone is also fine, we have many chapters ahead. To present, just check out the list of the chapters. Feel free to select anyone you are willing to present. Right. Okay. So thank you very much, Jacob. Thank you, Darren, and thank you everyone that joined us today. And we see
you for organizing it. Thank you for organizing all these meetings. And Darren, I'm very much looking forward to next week.
Okay, well, I'll do what I can.
All right.
All right, guys.
Bye. See you. Bye.